Hello to everyone, I am Luca Ciccone, and in this talk, I'm going to show the application of inference systems with Corules for defining first subtyping and liveness properties of binary session types. This is the outline of my presentation. I will start with the main motivations and an overview of the properties that we're interested in. Then I will introduce the framework that we're going to use, that are inference systems and their generalization with Corules. And at last, I will move to the main topic of the discussion, that are session types and their properties. So our aim was to apply inference systems in the context of session types, in order to define in a compact way properties that require a mix of induction and co-induction. Hence, considering inference system, we used their generalization with Corules. And at last, we aimed at formalizing all the results in Agda. Starting from the properties of concurrent systems are usually divided in safety and liveness ones. Safety properties are informally identified by the motto something bad will never happen. This means that they are based on an invariance argument, because we want that at each state some property holds. Hence, they require a co-inductive reasoning. On the other hand, liveness properties are identified by the motto something good will eventually happen. So they are based on a well-foundedness argument, because we want that eventually some property hold. Hence, they require an inductive reason. Actually, there exist some properties that mix both safety and liveness, and hence they require a mix of the approaches. Inference systems are a framework for defining predicates. And in particular, they come with the pure inductive and co-inductive interpretation for dealing with inductive and co-inductive predicates respectively. They are used because they provide canonical ways for proving the correctness of our definitions with respect to some set of judgments that we assume to be valid, and this set is called specification. In this case, we can rely on the induction and co-induction principles. They have been recently extended with Corules, so that now we are able to express properties in which induction and co-induction are mixed. So they seem to be the right tool to be applied in our context. More in detail, given a universe U of elements that are called judgments, an inference system I is a set of rules that are pairs, premises, consequence, such that both the premises and the consequence lie in the universe. They are usually presented in a finite way using meta rules that group together rules according to their schema. Then we say that a proof tree is a tree whose nodes are judgments in the universe, and there exists a node C with set of children PR if there exists a corresponding rule PRC in the inference system. Then a proof tree for a judgment J is a proof tree rooted in J. From a definition, then we have to take an interpretation. The inductive interpretation is the set of judgments with a finite proof tree. The co-inductive interpretation is the set of judgments with a possibly infinite proof tree. Before introducing Corules, I show a paradigmatic example, which is maxelem. This predicate holds if M is the maximum of the potentially infinite list excess. And this is the first example of a property that requires a mix of induction and co-induction. On the one hand, first of all, we require that M is greater than all the elements of the list. On the other hand, M must belong to the list. This is a definition given for inference system. It consists of a couple of meta rules. In particular, the first one is a meta axiom. The axiom states that X is the maximum of the list containing only X, and lambda represents the empty list. The meta rule states that if Y is the maximum of the list XS, and we add a new element x to xs, then the new maximum will be z, which is the maximum between the old one and the new element. But then we have to take an interpretation. And the inductive interpretation is sound but not complete. For example, we cannot derive judgments, valid judgments on infinite list. For example, we cannot state that 1 is the maximum of the infinite list made of ones, because we can deal only with finite proof trees. On the other hand, the coinductive interpretation is complete but not sound. In particular, we can derive statement like 5 is the maximum of the infinite list made of 1, 2, 1, 2, 1, and so on. More in general, we can state that the maximum of a list is any number which is greater than the real maximum, but that at the same time does not belong to the list. To solve this problem, we introduce Corules. And in this case, in particular, we introduce a coaxiom. The axiom simply forces the membership of the element into the list. The obtained interpretation is called interpretation generated by Corules, and it consists of the judgments with a possibly infinite proof tree in the coinductive interpretation of the inference system without the Corules. But then we ask that each node must have a finite proof tree in the inductive interpretation of the whole inference system. So in this case, we consider Corules as normal rules. In this case, we can rely on the bounded coinduction principle for proving the completeness of the definition. Coming back to the max example, assuming that we want to derive judgment like 2 is the maximum of the infinite list 1, 2, 1, 2, and so on. Here on the left, we can see an infinite proof tree in the coinductive interpretation. In fact, we apply infinite times the rule. Here on the right, we can find an example of a finite proof tree in the inductive interpretation of the whole inference system. In fact, we apply the rule once, and then we apply the coaxiom. Then if we consider again the example 5 is the maximum of the same list, in this case, we can provide an infinite proof tree in the coinductive interpretation, again applying infinite times the rule, but then we are not able to provide a finite proof tree in the inductive interpretation inside the extended inference system, because we will never meet 5 inside the list. Coming to the main point of this talk, I'm going to introduce session types. Session types are a formalism that are used for specifying communication protocols. And here you can see some examples. The first one are models a process that can receive true and continue as are, or receive false and terminate. This construct is called branch. The second example models a process that sends infinite times true. And the last example models a process that can either choose true and continue as t, or send false and terminate. And this construct is called the choice. This is how we decided to define session types in a coinductive way, because we consider also possibly infinite session types. And they can be nil, receive f, or send f, where f is a total function that we call continuation from some set of messages v to session types. Nil models an unusable channel. Now we can encode branches and choices construct that we saw in R and T by composing continuations because they are total functions. So in this case, we are able to compose, for example, a function f defined only on true and that as nil on false, with a function g that is defined on false and as nil on true. Actually, we decided to define session types in this way because we aimed at simplifying as much as possible the Agda formalization. And we are also able, in this case, to express dependent session types because we are using functions to compute the continuations of the session types. This is what happens on the Agda side. First of all, we have the main data type, that is session type. And the only thing that I would like to highlight here is that the constructor exactly corresponds to the definition that we saw before. And then we have the type of continuations that are functions from the set of messages V to the coinductive counterpart of session type. Before coming to the properties, we need a few more notions. And here you can see the label transition system for session types. It consists of a couple of rules. The first one says that receive F goes to F of X, receiving X. This is an action. And send F goes to F of X, sending X, provided that X is in the domain of F. The domain of a continuation is the set of session types that are different from nil. And this is required here because the action of sending is an active action. So these rules are not symmetric. Hence, nil models an unusable channel. If we compose it with input and output operations, we can model impossible outputs and unexpected inputs. So we say that the process has successfully terminated if it has the form send empty continuation, because this session type cannot reduce anymore. On the other hand, receive empty continuation can still go to nil if it receives an unexpected message. To conclude, here we can see the reduction rule for sessions. And a session is composed by a pair of session types using this parallel operator. On the left, there is a client, and on the right, there is a service. A session models a system in which two processes want to communicate. So we have that S, T goes to S prime, T prime, if S goes to S prime and T goes to T prime, where the actions involved must be complemented. This means that they are both, that they consider both the same message, but the polarities are swapped. And then we consider the reflexive transitive closure of the reduction. Now I'm going to informally introduce all the properties that we studied. The first one is weak termination. And actually, I'm not going to give more details about it in this presentation because it is the simplest one. Weak termination means that a session type T preserves the possibility of successfully terminating along all of its transitions. And this is the first example of a property that mixes safety and liveness. In fact, we ask that the set of session types identified by the statement above is closed by transitions. And on the other hand, each element of the set must be able to reach successful termination. The second property that we consider is fair compliance, which involves sessions. In this case, we say that T is fair compliant with respect to S if the session TS preserves the possibility of reaching a state in which T successfully terminates and S does not fail. Again, the set identified by the definition, which is composed by pairs of session types, is closed by session transitions. And at the same time, it must be always possible to finally reach a state in which the client successfully terminates and the service does not fail. To conclude, we consider fair subtyping, which is a different kind of property. It states that T is a fair subtype of S if R fair compliant with T implies R fair compliant with S for every client R. And this is a liveness preserving property, as we will see in a while. Starting from the fair compliance, I'm going to introduce its unfair counterpart. We say that T is compliant with S if the session TS reduces to T prime S prime and the session T prime S prime does not reduce anymore, this implies that T prime successfully terminated and S prime has not failed. This is an example of a safety property because at each step of the interaction, it must be possible either to synchronize or we reached client satisfaction. Fair compliance states that the session TS, no matter how T and S interact, it is always possible to find a finite extension of the interaction that leads to the client satisfaction. And here you can see a couple of examples involving the session types that I introduced at the beginning of the section. We can prove that R is fair compliant with T because T is always able to send false, and in that case, R successfully terminates. On the other hand, this is not possible if we consider S, because S cannot send false. Hence, R will never be satisfied. So R and S are compliant, but not fair compliant. This is the definition given for inference system. It consists of 3 meta-rules and a couple of corules. We have an axiom that models the desired state in which the client successfully terminates. And then we have the 2 rules that model the interaction between an input and an output and vice versa. In each rule, we have this side condition that asks that the domain of the function of the continuation involved in the output must be non-empty in order to guarantee the progress of the interaction. The difference between the corules and the rules is that in the rules, we have a premise for each element in the domain of the continuation involved in the output, while in the corules, we have only a single premise. In this case, we managed to prove that the coinductive interpretation of the inference system without corules is sound and complete with respect to the compliance relation, while the interpretation generated by corules of the whole inference system is sound and complete with respect to fair compliance. In order to give an idea of how the rules are used in the proofs, we can consider, for example, the soundness proofs, where we start from the proof that our definition holds, and then we have to find a finite interaction extension leading to the desired state. And this is possible by induction over the proof inside the inductive interpretation of the whole inference system. And in that case, the base case is the axiom. So coming back to the examples that I introduced before, we have that R and S are in the conductive interpretation of the inference system, but not in the interpretation generated by the corules, because we are not able to find a finite proof tree in the inductive interpretation. We are only able to express infinite proof trees by applying infinite times the rules. R and T, on the other hand, belong to the interpretation generated by corules because, as you can see, here we can apply the corule to consider only the branch leading to the desired state in which R successfully terminates. Moving to fair subtyping, again, I introduce its unfair counterpart. We say that T is a subtype of S if R compliant with T implies R compliant with S for every client R, and this corresponds to Guy and Dole subtyping. Fair subtyping states that T is a fair subtype of S if R fair compliant with T implies R fair compliant with S. And so we call it a liveness preserving property. The general idea is that a process that behaves according to T can be substituted with a process that behaves according to S without compromising fair compliance. Again, we can consider a couple of examples and assume that we want to relate T and S. First of all, we have to know that subtyping is contravariant in outputs. So here T and S are subtype. T is a subtype of S. The problem is that T is not a fair subtype of S, because in the previous slides, we found that A, which is a client fair compliant with T, is not fair compliant with S. Hence, T is not a fair subtype of S. On the other hand, we can consider another example, T prime, that is similar to T, but it sends an even number of true. In this case, we can prove that T is a fair subtype of T prime. For example, A is fair compliant both with T and T prime. This is a definition given through Inference System. In this case, we have 4 meta-rules and a single corule, which is complicated, and I'm not going to give details about it. The first axiom nil states that nil is a fair subtype of any session type, and this holds because there are no clients that are fair compliant with nil. Then we have that AND is a fair subtype of a session type different from nil. Again, this holds because a client which is fair compliant with AND already reached the desired state. And then we have 2 rules that models the invariance and the covariance, respectively, of input and output. Invariance and contravariance are dealt with using these side conditions that involve domain inclusions of the continuations. In this case, we managed to prove, similarly to the fair compliance, that the coinductive interpretation of the inference system without the corule converge is sound and complete with respect to subtyping, while the interpretation generated by corules is sound and complete with respect to fair subtyping. Again, if we consider the examples that we saw before, we have that T and S do not belong to the interpretation generated by corules because we are not able to find finite proof trees in the inductive interpretation, while T and T prime, since T is a fair subtype of T prime, they belong to the interpretation generated by corules. Summarizing, we started from the properties of concurrent systems, and we saw that they are usually divided in safety and liveness ones. Safety properties are based on a coinductive reasoning, while liveness ones are based on inductive reasoning. The properties that we are interested in are those involving a mix of the approaches. So we introduced generalized inference systems that are a framework for dealing with predicates that mix both induction and coinduction. And at last, we managed to provide compact definitions of fair compliance and fair subtyping, and all those definitions involve single inference systems. As I said at the beginning, we formalized all the results in Agda, and we recently developed a library in Agda for dealing with inference systems and their generalization with corule, and we presented it at ITP this year. And if you are interested in looking at the code, you may want to know that the set of values is at the moment fixed to Booleans because we are able only to express meta-rules with a finite number of premises. So as an ongoing work, we are updating the library, first of all, to deal with the issue that I just mentioned, so that meta-rules can have infinite number of premises. And then we also want to model the dependency between meta variables and the number of premises. Then we would like to generalize all the formalization to arbitrary set of messages V, and doing that has the advantage that then the code directly reflects the presented definition given through Inference System. Then we are working on a type system in order to reason about liveness properties of processes. We are considering also delegation in fair subtyping that we didn't mention in the previous slides. Here you can find the links both of the library and the formalization. If you would like to use the library and you have any questions, feel free to contact me. Thank you for watching this presentation.